Hello, everyone. Today we are going to talk about estimation, which is chapter 5. Um, so far, you guys have learned the normal distribution, sampling distribution, and now we are learning estimation. And after this estimation chapter, you guys gonna learn hypothesis testing for like the next 2 weeks. After that, we're gonna have second exam. The exam will cover chapter 6 through 10. Okay. This chapter is very important because it will give you the connection of using some kinds of distributions and statistics, why we are even interested in statistics and how the distributions play the role here. So estimation is like something you're trying to estimate, like average, the mean gas price in New York State or average income in of household in New York State, or a percentage of unemployment rate, or any kinds of thing. So you look at like a statistic, the GDP grows some percentage or whatever, those are our estimation. So hypothesis testing is like, which we're gonna talk about in next couple of weeks is, um, for example, we are testing where our estimation is correct or not. Example is, okay, is the mean gas price higher than $2 per gallon in the New York State or not? So we are testing this against some hypothesis using some data. So those are the things we're gonna do in, excuse me, oh sorry. We're gonna do it. So another example, something relevant to economic is, okay, is the defective rate lower than 1%? Something like that. So some terminologies, you guys already learned this. Population is just a set of subjects that we want to study. So for example, we want to study the unemployment rate, the of whole population in the US. Those are basically population, basically the subject we want to study. But the problem is we cannot assess all the people. So we are using some kinds of a sample in the observed subject that we are, based on them, we are just trying to get some estimation. So the parameter is the numerical measures associated with the population. It's constant but unknown. For example, the actual unemployment rate of US people and people who live in US, those are like a actual parameter. It's constant, fixed, whatever number, but it's not known because we never ask everyone. In other words, but we are using sample to estimate those actual parameters. So this is random but known. Something like um, for US unemployment rate, they are asking some fraction of people by choosing some random sample and asking, are you employed or not? So they are using subsample to estimate the unemployment rate. That is statistic. So example of a parameter is mean gas price in New York State, and population is all gas station in the New York State. But since we cannot get all the station, we are having, for example, 10 random sample, or even higher than 20, or 100, etc. Parameter is a defect rate of a manufacturer. That those are something we want to interest in. So to get the actual parameter, we can use population, but we can use sample. For example, manufacturing company, they are producing millions of product a day. We cannot check the defective rate of millions of products. Instead, we are choosing random sample of couple hundred, even couple thousand, and just trying to get the defective rate. Those are the benefit of sampling. So one more question is, you want to estimate the result of a presidential election based on poll. So what is not correct? So just take a look at that and let me know. So you guys might want to pause and just answer it. So estimation is a guess. to guess a parameter by statistic. So we are trying ultimately want to know the parameter, but using some kind of statistic. This is called estimator. So we are trying to guess the real true, a parameter, true value that we want to know, but we are using sample to estimate that. Those are called statistic or estimators. So for example, parameters we want to know is mean guess price, defective rate, the percentage of vote, but estimator is a sample mean of guess price or fraction of defective products among inspected. In other words, it's among sample, right? So percentage of survey, this is another sample. So we are trying to guess a parameter using some samples. Those are called estimator. So this is a data is usually a notation for the parameter of interest. It's something we want to know. Mean guess price or defective rate, fraction of votes. Those are or parameter of interest, but unknown. It's not random. Any aspect of population can be the parameter of interest. So by mean, you can get expected value of x, variance of x, and probability of some of this. So remember the data is an aspect of population. So what cannot be data? So again, you might want to spend some time on this. I'm gonna leave you the answer. So please pause this video and try to answer it. So answer is C, the total number of heads when 10 coins are tossed, because it's a sample, not a population. So it can be different if you throw a coin again. So maybe when you throw the coin 10 times, the number of heads might be 7, but next time will be 6, or it might change, it might be 10 out of 10, something. It changes every time you throw the coin, right? So those are the characteristics of this. So it can be different if you throw the coin again. And a random object cannot be parameter of interest. So it shouldn't be random. So whether they have a random or not is an important thing in here. So data head, this head thing, previously we said that this data is a parameter, but you have a head, this little, like a cap shape. This one is called head. That is on that indicates, okay, we are trying to get try to estimate the true parameter. That is an estimator for data. This is how we use in statistic. It's random because we are using samples to estimate this. So true parameter is not random as we discussed, but since we cannot get the whole population, we are trying to use random samples to estimate these parameters. So this is a core estimator for data. It's random. So we have a very good property, expected value of data. For example, for data equal E of x, expected value of x, there are many estimators. Sample mean after deleting mean, and max to deleting some outliers, and sample median, etc., etc. So let data be the mean of gas price in New York. So let's say you observe 100 gas stations. What cannot be the estimator for data? So again, you might want to take a look at. So this is number, something like that, or sample variance, or population mean, or price near the gas station. What cannot be the estimator? So let's take a look at. Answer is D, because mu the mean value is from population. That is unknown. We learned this in previous chapter in 2, because this notation is for population average. But when you have an X bar, that was a sample average, right? So any available number can be an estimator. So we need some criteria to evaluate estimators. Usually we consider expected value of some sample estimator equal to true parameter. This is actually very important property. When you guys are gonna take a little more advanced statistic, this is something you're gonna learn in detail. So that is called law of large number. I probably briefly touch later, but this is very important property. So as sample size increase, your true, sample parameter will be very close to data, true parameter. So variance of data will be, as variance of data smaller is better. So unbiasedness is another thing, a very important property. So a bias is like, let's say bias, the concept of bias is like that. So let's say you're trying to get the unemployment rate. Let's say the true unemployment data is like 7%. I just made a number, but we use some samples. So we estimate using sample. This is from population, and this is using sample. We are getting 7.3% somehow, let's say. But what is the bias here? So bias is always this data hat minus data. So that is, or we usually say expected value of this minus this equal basically 0.3%. This is a bias. Types of, concept of bias. So why this is important? Because we don't want to have any bias in our estimation, because bias creates some error, error kinds of things. So we never want that happen. So that's why we don't want that. But our concept of bias is like that. So expected value of data head minus data is the bias of the estimator. So if a bias is positive, then it's overestimated. So in our case, we had a 7.3 as the example for unemployment rate, and basically we are overestimating. But if it's negative, let's say 6.9, then we are underestimating by 0.1. So bias is 0 when these are equal each other, because subtraction would give you 0. That is called unbiased parameter estimation. Very important concept. I will come back. So biased estimators distribution is like that. For example, this is our true parameter, but let's say this is our true parameter, but somehow we were getting this is whatever value we are interested in. So basically, this is biased because this is like a data head. But let's say this is our true unemployment rate of 7%, but somehow I'm getting 6.5% or something like that. Then, I'm gonna have a bias. But this is, on the other hand, unbiased estimator. But notice something. Which one is more widely spreaded? It's this one. But this one has a lower variance, or spread is much smaller. Again, we said, smaller the better, right? But on the other hand, we also don't want to have any bias. So it's like a trade-off. This one has a smaller variance, which is good, but they have a bias, which is not good at all. So, but on the other hand, this one, it had no bias at all, but the variance is so high. So this is actually trade-off. In statistics, in general, you cannot have both in statistics. So it's like you need to trade off one or the other. So data head is more efficient than data bar when data head utilize more information in the sample than data bar. So efficient means, basically they are using more information. So their variance would be smaller. So this one would be more efficient in terms of variance. For example, mu head be the sample mean, and mu bar will be the sample mean using part of the observation, let's say. Because this one uses more information, of course, this will be more efficient. This is in statistics, if something is more efficient than the other, then they are using more information or more samples like that. So it is related to the variability of an estimator. If an estimator varies little or variance is small, the estimator is reliable. On the other hand, because outlier will have a similar effect on the estimator. So in other words, as the variance is smaller, it's more data is around this mean. So it's gonna be more reliable. But again, trade-offs. So efficient if variance is smaller. Smaller variance is good, or smaller standard deviation is good. That means it's efficient. So as variance is smaller, it's better. So this is actually graph visualization of the trade-off I talk about. For example, this is like unbiased and precise. So this is the best option, unbiased and precise. But this one, unbiased but imprecise, or they have a higher variance. So variance on this side, this first column would be smaller than in the second column. On the other hand, this one has bias, but variance is small. This one has bias and imprecise, large variance. This is the worst, but in most of the cases in statistics, you're gonna talk about this second one and the third one. So there are already trade-offs, as we discussed in our previous graph. This one, imprecise, unbiased, but this is biased, precise. So you guys think which one would be better? So let's say X bar is an estimator for mu. So again, mu is something we are trying to estimate. This is a population parameter, right? And X bar is using sample, we are getting average. I mean, we learned this in detail in the third chapter. So mu was a true population parameter from population, like unemployment rate of 7%, which I just made up, but let's say that is true. But this X bar is using sample. So what we want to know is expected value of X bar is equal mu. So this is one of the property, which I'm not gonna cover in detail, but if these are equal, then it's gonna be unbiased because the difference would be 0. Again, in a couple slides ago, if the difference would be biased, right? But if this are the equal, then in other words, the difference equals 0, then they are unbiased. And this was the formula for variance. So that was variance of X was sigma square, but variance of X bar was sigma square over N. This is important distinction, variance of X and variance of X bar, okay? We learned this in chapter 4. So just, take a look at that if you don't remember. I derived how to get this in detail. So if we have a sample variance, we are using 1 over n minus 1, okay? And if it's unbiased, our sample variance would be equal population variance. But if we do the math, so it's gonna be biased. So a little bit of a trade-off, which I explained in here. Usually you are trading up a second one and third one. So let's look at some example of a bad estimator. So we hope to estimate mean gas price in New York State. So we observe gas price at 100 station. Let's say X bar, just I'm thinking X bar is too small. So define estimator of this. What is the problem with all this? So take a look at that. So I'm gonna move to the next section. So try to look at that. Okay, you might wanna pause it. So expected value of this mu bar equal expected value of X bar plus 1, which is here because we know E of X bar equal mu in here over here, right? So you just plug in the math because let me show you why. So I said initially mu hat equal X bar plus 1. So take the expected value in the both sides, which is here. but expected value of x bar plus 1 equal just expected value of x bar plus 1. So this is how we derive. Okay. Okay. Oops. So this is this, but it's efficient as this one equal this. So as you can see, there are some trade-offs, you know. Because variance of this equal, so variance of x bar plus variance of 1, but variance of 1 equal is 0, so these two are the same because the scalar doesn't have any variability, no randomness in here, so variance of 1 equal 0, so that's why these are equal by the definition from here over here, so it's gonna be like that, okay? This is another types of example. I do not want to calculate the mean of this, so I just use average of two observations. So we can view mu tilde as a sample average of the two. So these are the two examples. But thing is, mu tilde is unbiased but less efficient than x bar because sigma square over 2, you know, I mean, this is a variance of mu tilde. Let's say, variance of mu tilde equals sigma square over 2 because this is sample size. Let's say you're comparing this with the sample size of 100. That was sigma square of 100. Which one is bigger? This is bigger. In other words, this is more efficient. So it's less efficient, but you know, again, this one is unbiased because I'm gonna show you why. Mathematically, I said mu tilde equal x1 plus x2 over 2. So take the expectation as in that here. So it's gonna be what? It's gonna be so 2 can come out. So it's gonna be 1 over 2, and you can separate them out. So it's gonna be expected value of x1 plus expected value of x2. This one was what? This one was mu. This one was mu, right? By definition. And we have 2 mu. Divide by 2 equal what? Just mu. So this one equal this. In other words, difference is 0. So no unbiased. So unbiased. Unbiased, but not efficient. So as you can see, trade-offs again, it appear again in here. So those are very important distinction. So that those were the examples. So you know, I was dishonest and late, so I just add one. So it's biased and inefficient. It's worst case. So which was this case. So just, I mean, try to do some math, whether you are getting the similar result I do. So, you know, this was the one of the example, I mean, it's biased, and on top of that, it is inefficient. So check out why this is the case. This is biased because expected value of this minus mu equal 1, so positive bias over estimation. So, but on the other hand, variance is very large, so this is gonna be inefficient. So worst case. So unbiasedness and inefficient is the top priority. So choose your correct statement. Take a look at this and definitely have some, take your time and try to get this, okay? So these are very important when you go to, you know, I mean, thinking to take econometrics, for example. These properties, you're gonna learn this again. I'm trying to cover this as fast as possible so that we can go to regression part later. But every single point in here is very important concept for you to know. So take a look at that. And if you guys have a question, please let me know, okay? So minimum variance biased estimator. So X bar is the best estimator for mu because there is no estimator satisfying both of the following conditions. So there is no condition that satisfies biasness, unbiasedness, more efficient. So you guys got to have some kinds of trade-off. So hence we focus on just X bar. So what we have learned so far is population and sample, parameter and statistic. and unbiasedness and efficient. Those are the things that we have learned so far today, right? So sample mean is the best estimator for the population mean. Let's talk about some kinds of example. Suppose that you are pregnant, or your wife. The due date was February 15. However, the probability that the baby will be born on this is not high. I'm not sure whether you guys have the experience, but doctor might say the due date is February 15, but it's gonna be around the 15, but it's not gonna be exact. It might be exactly 15, but it's gonna be some kinds of probably associated with that. It might be earlier, a little bit later, etc., etc. So in fact, the estimate is somehow useless because until when can she work? So is it okay to schedule a business travel on February 10? So this is another kind of example, So let's say interval estimation. So point estimation is another example, like a February 15 is a point estimation. You are estimating exactly point, but interval on the other hand, it's like between February 10 to February 20. So this is example that, okay, Dr. Mai said, with 90% of a chance, you're gonna, have the baby around this interval time. So instead of having exact point, your doctor might say, okay, it might be sometime around here, But the drawback of a point estimation, it doesn't have anything about precision, but this is more realistic. It reflects potential error in the estimator. So we are talking about some kind of probability, with some 90% or 95% on probability it's going to be happening. So this is interval estimations. Okay. So I'm gonna stop the video here a little bit and then come back to this point. You guys wanna listen to the following video, okay? Thank you.